Now that we've got some networks ready for flux balance analysis, we want to actually perform some. So we can see here we've got the two networks that I made earlier, one ready for flux balance analysis and one not ready for flux balance analysis. And actually here I have changed something. I've saved the first one in level 2 version 1, so now everything's in level 2 version 1 SBML, so it's compatible with the Cobra toolbox. So if we load MetNetMaker up, we see that it keeps the same reactions as it had when it was last closed. And actually I don't have the Cobra toolbox on this computer, so I've logged into my other computer where I have all of the same files synchronized to it, and this is where I'm going to perform the flux balance analysis in the Cobra toolbox. So let's load up MATLAB, and the first thing we'll do is load in the network which has not been prepared for flux balance analysis. So that's just the top of glycolysis model. So that quickly loads in. And then we use the optimized constraints based model function within the Cobra toolbox, and we see that on the unprepared model the flux through the objective function, that's what's given by F, is 0, and we see that the flux through all of the reactions is 0. So the next thing for us to do is to load in the model that we have prepared for flux balance analysis, and we can call this B here. So here we go, we've got B in, and we want to also use the optimized constraints based model technique on B, but this time this is a model that has been prepared for flux balance analysis. And so what we see is that the flux through the objective function is 50, which was the maximum constrained amount when we created the model in MetNetMaker. And obviously you could change that amount and see what happens, but we also see that there are fluxes through the majority of the reactions within the network. Now this is really good. So what we can go is move on to the next stage of flux balance analysis, some kind of application of it beyond simple analysis of a network, move on to actually looking at what happens when we make changes to the network. So on the Wikipedia site for flux balance analysis, there are two examples of gene deletions where a reaction is removed from the network, both a lethal and a non-lethal gene deletion. And we want to try and recreate these and see what effect that has. So let's keep that picture up there whilst we load up the network in MetNetMaker. And we're going to remove the reaction from alpha D glucose to alpha D glucose 6-phosphate. So we just click on the box on the left, press delete, and we can delete the reaction. So there we go, it's deleted, and we will export this as a level 2 version 1 SBML file, which we'll save so that we know that this is the non-lethal gene deletion. So this is the non-lethal gene deletion, and it's obviously an XML file because this is the SBML export. So I'd best just change that. There we go. Save that. And now that we've deleted the reaction, we can't get it back. We could add it back, but actually we can just delete all the reactions and reload the model that we know is ready for FBA. So just get back to where we were before. Just load that in. And now we can move to delete the reaction that we know will break the network. So is this reaction here, beta D fructose 6-phosphate to beta D fructose 1,6-bisphosphate. We delete that reaction and export it as an SBML file again. So now we want to take those two reactions two networks that we've just created and see what they do in the Cobra toolbox. So we don't want to actually load it in as model B. Let's load it in as model C. And let's start with the lethal gene deletion one. So we will load in to the Cobra toolbox in MATLAB as Model C. We will load in the network that we've just created that has the lethal deletion. Okay. And again, we'll use the optimize constraint based model function within the Cobra toolbox, but on Model C, to see what happens here. And what we see is that the flux through the objective function is 0, and when we look at the fluxes through all of the functions, there are some fluxes, but none of them are through the objective function, and in fact they're just in and out of the network rather than actually doing anything within the network. So we now load the non-lethal deletion in as Model D, perform the same optimization, the same flux balance analysis on this system, but this time it's the D model, the non-lethal deletion model, and what we find is that the flux through the objective function is now 50, the maximum constrained amount. And so we look at the fluxes through all the reactions in this case, and we see that they're pretty similar to the case where there were no deletions.